Ready to go? Yeah, we are. All right. All right. Thanks, everybody, for coming. I'm Charlie Bracken. For about the next hour, I've put together a presentation for you on understanding signal, noise, and resolution in astroimaging. I've put the emphasis a little bit on understanding. There are some equations in here. We are going to do some math, but I don't see the reason to sort of go into too much of the math. This isn't calculating signal and noise as much as sort of trying to develop a little bit of an intuitive understanding. So if you've done imaging, you've probably seen a lot of these concepts before. My goal here is to try to present them, step through them in a manner that gives a better intuition for the way things work. So really fast, I live like 10 miles from here. These are the scopes that I currently shoot with the most. These are two William Optics Star 71s. I chose them because they're small enough that I can put them next to each other on a reasonable size mount. They have an excellent flat field, great for wide field narrowband imaging, which is the majority of what I do. Being in the light polluted skies of New Jersey, that's just where you sort of almost have to go. You can see the light pollution there. That's in my neighborhood. I shoot from my front yard, and you can see that basically the first 30 degrees of the sky at least are just, and that's actually looking west. That's my good side of the sky. The entire east side is the New York City light dome, so that's just a complete washout. And I've written 2 books on the subject. In 2013, I published the Deep Sky Imaging Primer, which is where a lot of the diagrams come from in this presentation. And then the Astrophotography Sky Atlas, which I tell people is an atlas of really, really dim things that might not be plotted elsewhere. So a little bit about the equipment. So this is the evolution that I've gone through over the past 7-ish years in astrophotography. I started off with a 7-inch Meade Maxitoff Cassegrain. This was the scope that I always wanted when I saw it in the magazines, you know, Astronomy and Sky and Telescope years ago. It just looked beautiful, right? That giant meniscus lens on the front. I always wanted one. And when I moved to New Jersey and got my first signing bonus with my job here, I said, I'm going to go buy my dream scope. And I also thought I was going to image with it. But at f/15, it is really not an ideal scope for imaging. I tried that. Jupiter looks great through it. Tried a little bit looking at a DSLR up to it. Didn't work out so well. I moved to a Meade 8-inch Schmidt Cassegrain. That was a lot of fun. I had a generic 102 millimeter Astro, I think it was Astro Telescopes was the brand I bought off eBay. It was a decent 102 millimeter f7. I had a not listed on here. I had a Eon 120 from Orion, which I really liked. Then I got the Teleview MP101. I missed that scope. I especially missed, and I show on here, taking it to f4 with the focal reducer. That was really eye-opening. Shooting at f4 was like a whole different thing. So then from there on, and you can see the trend here of sort of faster and faster focal ratios. I had the Borg 77 ED2, which was super fast at f4 as well. I had an Astrotech AT8RC. I had a reducer for that. Actually, I'm moving, so I just recently sold that one. But that's one I'm probably going to buy back. That's for sort of the long focal length imaging. That's a really good scope. Love the fact it stayed in collimation all the time. Like, it was just so easy to deal with. Right now, my main scopes are those 2 William Optics Star 71s. They're mounted right next to each other. I've got them aligned so I can tweak the alignment and basically get twice as many hours per night. So on a good winter night, I can actually capture up to 20 hours of total exposure time, which is really nice to have, given how infrequently you get a nice clear night. Takahashi FSQ 106, that is just a dream scope. It's unbelievably sharp. Love that scope. That's also one of my go-to scopes. And then I actually just bought a Samyang 135, which is a surprisingly good long telephoto lens, manual focus, and it goes to f2, which is, and it's good down to about f2.8. My mounts, so if the trend in scopes is faster and faster optics, in mounts, it's steadier and steadier. I started out with a cheap Meade LX75. You're throwing out a whole lot of subs with that. Moved up to the C-Gem, and I was like, wow, I don't have to throw out all my subs. This is pretty good. And then I got the Takahashi just recently, and now I don't throw out any subs. That thing's just absolutely fantastic. Cameras, I started out with a Rebel XSI, the 450D by Canon. I self-modified that one. That actually was my go-to camera for the longest time. That was really nice. Got a lot of use out of that. Right now I shoot with two 8300 chip cameras, the QSI and the S-Big. Both actually are pretty old. That's the original ST8300. I've got narrowband filters on those, and I just recently got a Canon 5D, which I had Hap Griffin modify. I've gotten to use that a little bit, which has been a lot of fun. And then finally in processing, and the trend in cameras would be from uncooled to cooled. That was the big revelation there. Moving to a cooled chip was just wow. Again, like that one of those big quantum leaps. Processing, Deep Sky Stacker, Photoshop, but most of the processing I do now in PixInsight. Photoshop's just sort of for cleanup at the end. So that's been my trend. I think this is a fairly common theme, and you're actually going to see these themes sort of pulled through a little bit. Those trends of faster optics, steadier mount, and cooled chips are really important in astrophotography, and we're going to talk about why. So this is our journey today. We're going to start off with poor Mr. Poisson. We're going to tell the story of Siméon Denis Poisson, and the guy just doesn't get a lot of love as a mathematician, but some of his work really undermines a lot of what we do. Signal to noise ratio in a perfect world, then signal to noise ratio in the real world, two very different things. Then we'll move into two dimensions from there and go into resolution and sampling, focal ratio, and then finally I'll try to summarize all of this with sort of a few key takeaways. So let's start off with poor Mr. Poisson. In 1818, the French Academy of Sciences wanted to understand once and for all what is the nature of light. So Newton had said it's corpuscular. It is composed of some kind of particle. And Siméon Denis Poisson agreed with that. He was a member of the Academy. A young upstart named Fresnel, famous for his lenses, submitted a very long abstract to the Academy saying, with all of this mathematics, this shows that light is not a particle. It is indeed composed of waves. So Poisson read through it. He was one of the best mathematicians in the Academy. Struggles through all of this because I think Fresnel was probably the better mathematician, but says, I've gone through your equations, and there's a fatal flaw. If what you say is true, then in the middle of a circular shadow, you should see a bright spot due to the interference of light. And nobody sees that. Therefore, light is a particle. The Academy ordered that the experiment be done, and they cast a perfect tiny sphere and a pinpoint source of light. And literally within weeks, they did the experiment, and they saw what is now called the Poisson spot. So Poisson is now embarrassed by this, of course. The young upstart has proven him wrong, and literally for almost the next 100 years, the matter was settled. Light was a wave. There were no particles. That is until this guy, in 1905, basically led us to the understanding that actually both of them are right. In a way, there's a wave nature, there is a particle nature to light, and for our talk today, it's important that we're going to consider light as particles. We're going to be thinking about photons, because what we do as astronomical imagers is count photons, which is a pretty extraordinary thing when you think about it. So I took one of my images, and I went back and I did the back of the envelope math to sort of say, how many photons exactly am I catching here? And this is a fairly wide angle. I think this is with the FSQ. And this is when I had an STL 11,000, so it's got pretty big, photo sites on it. And I said, how many photons, if I back calculate this out, am I getting? And in the sort of medium brightness area there, it's about 45 per minute per photosite. In the slightly dimmer area, 42. So as astro imagers, we deal with things that the normal photographer in daylight can't even imagine, right? The things that you have to deal with to count 42 photons a minute accurately and distinguish that from 45 photons is pretty astonishing, right? So this is what we're faced with every clear night. Now, you know that if you take longer exposures, you get more photons, and you will get better images. Technically, I suppose I could end the talk here, right? If you just took that advice and said, just go get more photons, you're done. Like that's all you need to do. But that's not exactly the reason why that works. And it's more than just more photons in there. When you say that, that's really just a law of large numbers, right? So law of large numbers is that if you take a larger sample, then as you take a larger sample, the mean of the sample will approach the mean of the population. And that makes sense, right? You can't poll 10 people and find out who's going to win an election, right? If you want to find out who's going to win an election, you need to poll, several hundred people or several thousand people. The larger your sample, the more accurate that's going to be. All we're trying to do is estimate the long-term brightness or the long-term photon arrival rate from a patch of sky. So if we take a longer sample, we'll have a more accurate way to do that. So you can see here, this is 1 4-minute exposure, and I magnified a little bit of it there. And you can see that it doesn't look that great. But if you average 70 4-minute exposures, 280 minutes, you get a much smoother image because you're able to distinguish. You have a more accurate read on what the brightness level is, more accurate count of the photons. But what we actually mean, a little more nuanced way of looking at this, is really it's higher signal to noise ratio. It's not just about the number of photons. It's about the ratio of the number of photons you've captured to the noise that's inherent in that signal. Okay, so we're going to spend a lot of the talk talking about, like, okay, let's dive into the components of signal and noise ratio. But first we have to define noise. Noise is really just the uncertainty in a signal. If anybody's engineers, we could go into even more nuanced and mathematical ways of looking at it. But basically, noise is a measure of how certain you are that you've got an accurate measurement of a signal. Now, the main reason to talk about that is that when you first read some of these things, you think, wow, I see these examples, and you think, well, just cut out the noise, right? Trim out the noise part of this. When you do these calculations, well, if the signal's this much and the noise is this much, just trim it out. But it's not part of something that you can trim out. It's an inherent part of the measurement, right? It's a level of certainty. So what we measure noise with, the yardstick for it, the unit for it that we talk about, is a standard deviation. So you've all certainly seen at some point in your life the bell curve, right? So this is the Gaussian curve or the normal curve. You can imagine that this is any continuous variable. So this could be average height of men in America, right? And so I think the mean would be, instead of 100, it would be about 5'10". The standard deviation would be something like 2.5 inches. And you would be able to use the Gaussian curve and the equations behind it to say how many men in the United States are between 5'10" and 6'2". Or you could, you basically calculate the area under the curve, and that allows you to figure out, how many people, or the probability of people being in a certain range. Now, the standard deviation, we don't have to go into how to calculate it, but the standard deviation is the measure of how dispersed that is, how wide that curve is. So you can have a curve that is really narrow, so you can have the same mean, but you can have curves with high standard deviations that are really wide, which means, you got people who are 8 foot tall and people who are 3 foot tall, or you can have a population where everybody's between 5'11" and 6'1". But it's important to note that with the Gaussian distribution, you can have one mean and multiple standard deviations. You see this could be like a quality control graph, right? Like you could imagine, like you're manufacturing something and you're getting better, but you can have the same mean and just tighten that standard deviation around it. This is true for continuous variables. The problem, this doesn't work for discrete variables. This doesn't work when you're counting photons. The math doesn't work right. So enter Poisson again. 19 years later, Poisson publishes a very long, it's 250 pages, basically talking about, he's very interested in juries in France. So he goes back and he gets all the historical records for jury trials because they changed the law stating that rather from, out of a jury of 12, a 7 to 5 split is no longer enough to convict someone. It now has to be 8 to 4. So they changed this law. he's fascinated with, and deeply concerned about apparently, the mathematics of how that increase the rate of acquitting people who are guilty or decrease the rate of ensuring that people who are guilty are indeed found guilty. So he's interested in the type 1 and the type 2 errors. This is kind of the first time this has been done. So to be very clear, he was not interested at all in photons or anything like that, anything that we apply it to, but he ended up in the process of this inventing the mathematical framework for discrete processes. Right? So this is what the Poisson curve looks like. Looks just like the Gaussian distribution, right? The difference here, it's discrete. So the chances of, this will tell you the chances, if you have a mean of 100, the chance of getting some 85 event, right? And this is any event. So we think of like photons are coming in, right? And what's the chance that you get 85 of them in a minute if the long-term average is 100? That's how we're going to think about this. But this could be any discrete event. The famous one given was the first practical application was something about Prussian soldiers being kicked by mules and like literally analyzing how often that happened. And that was like the first practical application. I think it was after Poisson died that somebody else came up to use his distribution for. We're interested in photons. We'll keep talking about photons. The important point is these are razor thin, and Excel isn't plotting them perfectly, but imagine them to be infinitely thin because there is a probability of 85 photons arriving in a given minute. The probability of 85 and a half photons arriving is exactly 0. 85.2 doesn't matter. They only arrive, there's discrete events, you only have integers here. So the curve takes the shape of the Gaussian curve, especially as n grows. The Poisson distribution approaches a perfect Gaussian curve, but it remains discrete, right? So it's a comb pattern, right? There's just little tiny spikes in there. And the mathematics behind it is completely different. But thankfully for us, it's super simple. In the case of the Poisson distribution, the standard deviation is always the square root of the mean. Couldn't be easier. But it's only the square root of the mean. You can't have any other standard deviation. That's what's interesting about the Poisson distribution. And this is used to model discrete events of all kinds. So just to emphasize that point, on the left that's the Gaussian curve, right? So you can have any standard deviation you want. On the right I show, and I'm sure Poisson would love to know about this hundreds of years after his death. You can literally go in Excel and type Poisson.dist, and it has its own function, and it'll like nicely generate these for you. So you've been a successful mathematician if someday, hundreds of years later, Excel has a function named after your last name. You can type in Poisson, and it will generate the distribution curve for a mean of 100. And you can see right there, that's what the distribution curve for a mean of 100 looks like in blue. It has a standard deviation of 10. I also had Excel plot with a mean of 400. The standard deviation there is 20, square root of 400. It's very simple. You cannot have a discrete arrival event that follows a normal distribution, which would be Poisson, and have any other standard deviation. If the mean is 400, the standard deviation is 20. That is just the way it is for events. And what we mean by independent events, any kind of independent event is where the arrival of one thing or one event happening does not affect the outcome of another. So you couldn't say like, I think Wikipedia gives a great example where they say that if you were to measure students arriving into a cafeteria, that would not be independent events because more are going to come. There's an outside factor. More are going to come at lunchtime and at dinner time than any other time, right? So it's when you have truly independent events, and photon arrival is a truly independent event. So I just wanted to underscore that. So the photons don't line up regularly. There's going to be some, each time we take a sample, right, we take an exposure, we're taking a sample of what that long-term rate is, which is the true brightness of something. Each time we take that sample, it's going to be a little bit different because they're not following any order. They're not lining up like planes coming into Newark. They're just coming when they come. So we call that variation shot noise. And we measure it by the standard deviation. All the normal rules, if you know about the standard statistics of a Gaussian curve, within 2 standard deviations of the mean, 95% of your events are going to happen, right? That's all that still applies, but the square root of the mean is always the standard deviation. So that's enough about poor Poisson. Although he came out pretty well in the end, right? He's actually turns out to be at least half right on the particle nature of light. And he didn't know it, but after his death, the distribution that he was so fascinated with and created to study jury outcomes turns out to be the very thing that determines the statistics of those particles. So let's look at signal-to-noise ratio in a perfect world. So this is the classic example. I say classic because there's like a million examples of it on the internet. This is the we're going to look at one photosite. So this is the schematic in my book that I created to sort of illustrate how a photosite works. I know there are currently cameras out there where you don't need to take darks. There are currently cameras with insanely low read noise. We're going to assume that those things still exist. In 10 years, maybe you don't have to worry about them, but truthfully, you do still need to worry about most of those things. So this is kind of the classic view of how a photosite works. You can imagine this is a CCD, but it really doesn't make that much difference between a CMOS chip and a CCD chip. So photons strike the top of the photosite. Hopefully, as many of those as possible are converted into electrons. So, not converted, I guess that's not quite the right word, but trigger the discharge of an electron. There's not really a well, but you can imagine that there's a place where the charge is stored. They're not ping pong balls really, piling up underneath there. But if you have good, quantum efficiency is basically determining how many of those photons bounce off and how many generate an electron in the well. That's basically your quantum efficiency, and that's going to vary by the angle of approach of the photons. It's going to vary by their wavelength as well. So hopefully most of the photons that strike generate an electron in the well, and for our first example, we'll consider that all of them do. It's perfect. One photon equals one electron in the well. Then the analog to digital converter basically says, okay, I'm going to measure the charge there, because a charge is nothing but a bunch of electrons in a space. So I'm going to measure the amount of charge, and I'm going to convert that to a number. That number is then going to be stored, and that is the brightness level for that pixel in the final image. Right? This is the basic process. However, those photons don't line up regularly, as we saw, and as we're going to explore in a little more depth. So there's some shot noise associated with that. There's also another signal, right? There's the thermal noise that's coming in, right? So as the heat is agitating the silicon, you're going to get electrons generated that didn't come from photons on the outside, right? So you got the thermal signal. That's going to have shot noise too. That analog to digital converter, it's pretty good, but it's not perfect. It can make some errors, so that's essentially what read noise is. And then, actually, every pixel, you can't have it manufactured exactly the same, so they don't all respond to light at exactly the same level. So that's how you get pixel non-uniformity. That's just the small variations, but also the extreme variations, which are like the hot and cold pixels, right? So the world's not perfect, but let's assume for a little while that it is. So we're going to assume that we have a one-pixel camera. That camera is going to track a part of the sky perfectly. We said that one photon is always going to generate one electron. We're going to assume that we're in outer space, I guess. There's no sky glow. And let's pretend that we know, we're omniscient, we know that this patch of sky generates 500 photons per minute. All right? Perfect camera. We take a picture. We take a 1-minute exposure. Count the electrons. It's 490. Right? Again, each time you're going to take a picture, you're going to get a slightly different number because of shot noise. Nothing you can do about Mother Nature. That's just going to be the facts. So it's rarely going to be exactly 500, even though that we know in this example that the long-term rate is 500. So that's our best guess right now at the actual rate. Right? You take one photo, you get 490, you're going to say, that's my best guess right now what the actual rate is. So these other columns are in here because we're going to expand this later, but we counted 490 electrons. The square root of 490 is 22.1. That's our shot noise. So we're going to say our best guess is that it's going to vary plus or minus 22 each time we measure it, and that'd be 68% of the time. It's going to be plus or minus 44, 95% of the time, right? That's basically what a standard deviation is going to tell us. So we get an average rate of 490 coming in per minute right now because we only took a 1-minute exposure. And the signal-to-noise ratio is the noise, which is 22.1, right? Or 490 divided by 22.1, which is the noise. Well, because in this example, it's perfect, and it's always the square root, your signal-to-noise ratio actually turns out to be exactly the same as your noise each time because, right, it's the square root of the number. So that's with one exposure. What if we take 10? So you can see you're going to get slightly different numbers each time. We took 10 minutes total. We got 5,034 electrons. The square root of 5,034 is 71. That's our noise. We approached. We're getting closer. We're down to 503.4. That's our new best guess at what the brightness is. That's our best guess of the long-term average. Notice we're getting closer to the true value as we take a larger sample. And our signal-to-noise ratio went from, where were we? 22 to 71. So we took 10 times the exposure time, and we got just over a 3-fold improvement in our signal-to-noise ratio. And it turns out that's exactly what you'd expect. So that signal is growing faster than the shot noise is, right? So the shot noise is growing with the square root of the number. The signal is growing with the number. Therefore, our signal-to-noise ratio is growing with the square root of the number. So you are getting diminishing returns. But the square root of 10, somewhere around 3.1, we got about a 3.1-fold increase in our signal-to-noise ratio when we increased our total exposure time 10-fold. So the bottom line here is that signal-to-noise ratio improves in a perfect world with the square root of your exposure time. So if you want to double your signal-to-noise ratio, you need to take 4 times as many exposures or 4 times longer, however you do it. So you're always getting diminishing returns. If you've taken 50 hours on one target and you go to 100 hours, you don't get 2-fold improvement. You get 1.4. So unfortunately, that's not even true, because in the real world, there are other sources of noise. Things aren't as perfect as that 1-pixel example where everything works perfectly. So let's take another look at the same exposure, the same objects. Again, hypothetical, but let's look at it when we start adding other things in. So world's not perfect, right? You got all the shot noise, you got the read noise, but the biggest problem, you've got other signals. So you've got the photons coming from your target, but you've also got photons coming from sky glow, and you've got the thermal signal. You've got all these other signals. They've got their own shot noise, and you can't get rid of it. So sky glow, for most of us, is going to be the real problem. So this is a slightly more realistic exposure. Same object. We're omniscient. We know that 500 photons a minute are arriving from that object. But we count 1,161. Now, we don't know where all those photons come from. They don't come tagged, I'm from sky glow, I'm from your object, and I'm from thermal signal, right? We don't know how to separate those. But what's interesting is that our signal-to-noise ratio has gone way up. One exposure now, our signal-to-noise ratio is 34 instead of 22. That immediately tells you something's wrong. You're not going to get an improved signal-to-noise ratio just by adding in a bunch of junk, by adding in sky glow. So if we think about it, we know that about 500 of those photons came from our object. Let's say that we know in this example that we know where the photons came from. About 600 came from the sky glow. About 100 came from thermal signal. All 3 of those are now going to bring their own shot noise. Read noise, let's say it's 10, right? That's the small error that the analog to digital converter makes in trying to read it out. It's not perfect. That's a pretty reasonable noise. And then there's something called quantization error. We're not really going to consider that because it turns out to be, it's typically in almost all cases extremely insignificant. But basically, that comes from the imperfect matchup of the number of electrons that you can have in your well and the number of numbers you have to plug those into, right? So if you have a 16-bit analog to digital converter, it's only got about 65,000 numbers to put in. If your well is, let's say, 75,000 electrons, there are going to be times when you're going to read out two electrons difference and you're going to get the same number, right? So it's just like a rounding error, basically, is all quantization is. We're not going to worry about that. We're not going to talk about it any further, but it's typically insignificant. So our signal-to-noise ratio is not 34 in this case. If we think about it, the signal that we want is only about 500. Now we've got these other 2 signals. Now we're going to take those out later, right? The dark signal you're going to be able to take out. You're going to subtract that out in dark subtraction. You're going to take out the sky glow when you reset the black point in the final image, right? Because you're not going to have, this washed out background. You're going to pull that back, and all the pixels are going to sort of have this equal addition to all of them. So you're going to take those out later. But you're never going to get rid of the noise they brought. You don't know how to subtract that out. You don't know what the true rate is. So the noise that came with those never goes away. And that's why when you have a bright sky glow, it just totally ruins your image and makes everything look like it's a lot noisier than it should be. So we also have read noise. So in this case, we're going to take we know our shot noise. So the square root of 1161 was 34.1. So that was our shot noise from this. That's our perfect world noise. But actually, we know that the true noise value has about around 10 more electrons added to it. So the real noise level is probably more like about 44. And if we do the math there, our true signal, the signal that we actually want, divided by 44, which is our better estimate of the noise, we're down to a signal-to-noise ratio of 11. So we added sky glow in, and the sky glow in this case was about the same as our target photons, and it cut our signal-to-noise ratio in half. So another way to look at this, I'm a pretty visual learner. I like to plot it out. So in our first example, we only had this target signal. And with that target signal, it had a tiny error bar on it, right? So that error bar, in the case of this, right, this was the square root of 500. But now we've added in another signal, sky glow, that's 600. We've added in the thermal signal of 100. It's got its own, each of those have their own error bars on them. We're not certain about what the true value is, and each time we measure it, it's going to be a little different. And then you've got this pure error term, read noise. That's just error that just gets added on. That's your per exposure penalty, basically. The final readout that we get is on the far right. Now again, we don't know, the photons don't come labeled, so we don't know where they all came from, but we read out around 1200 with this larger error bar on it now. Right? So that error bar over there, which is sort of the noise, is larger than when we had a perfect world over here. Now, again, we're going to set the black point in the final image and do dark subtraction to hopefully take out our estimate of what the thermal signal was. So that we're going to be able to take that 100 out, but it's going to be slightly different each time. So we don't know exactly how much to take out, but we're going to make a good estimate of it. By taking lots of darks, we can make a good estimate. And the sky glow will take out through setting the black point. But not only are we still stuck with that larger error bar in the final purple part there, can't get rid of we can't make the error shrink. We also lost all this dynamic range, right? So those are wasted photons sitting in the well. That means that now you're not going to be able to get target signal from them. So if you fill up with sky glow, maybe even the medium brightness parts of your object are going to cause the well to overflow, and you're going to clip out. All right? So this is another way to sort of think of the same example. What's also interesting is square root of 500, our shot noise here is 22. Square root of 600, our shot noise is about 24. Our thermal signal, square root of 100 is obviously 10. Read noise is just 10, it's just noise. Our final value for the actual noise is 44. If you notice, 22, 24, 10, and 10 is 66, not 44. So this leads us to the insight that noise does not add normally, and that makes a lot of sense. So noise adds in quadrature, which is you just square each source of noise and then take the square root of the sum. And if you think about it for a second, that makes a lot of sense, because otherwise, if you had shot noise from one exposure, let's say you got 100 photons, the shot noise is 10, square root of 100, and you then took an exposure twice as long and you had 200 photons, it's going to be the square root of 200. It's not going to be the square root of 100 plus 100. You would get too large of a number that way, right? So we know that it's the noise is only growing with the square root. So to account for that, you have to look at noise logarithmically. It adds in quadrature. So, looking at that again, another way to look at this is to say, take the 500, take the 600, and take the 100, add them together, and take the square root of that. That's the exact same thing as squaring 22, squaring 24, squaring 10, adding them together, and then taking the square root. You'll get the same thing either way. And then the noise is a special term. It just goes on top. It's just icing on the cake. So that's how you get to 44. I don't want to put the emphasis too much on calculating noise. You're never really going to have to do that, but it does provide some insights into how our returns are. So if we do the same example really quickly, just like we did with the perfect world, in the imperfect world, we take 10 exposures. Right? So we're getting all of these exposures right around 1200. We take 10 minutes of exposures. We get 12,111 electrons, let's assume. The square root of that is about 110. But we've got to add in the read noise from 10 exposures. So we've got 10 electrons of read noise in each exposure. So we've got to add that all in. We end up actually closer to, and actually I'm looking at that, I think I did the math wrong. It should be about 120. This is what happens when you're editing your slides at the last minute. It should be about 120, right? But our signal to noise ratio, and actually I don't know the math exactly, somebody could do it, but it's not 110, it's probably somewhere closer to 40, right? But our average rate per minute, we're probably honing in on what the average rate per minute is of our target, our sky glow, and our thermal signal. We've got a good read on what the average of all those things are together, right? So, with other sources of noise, the rule pretty much holds. You still end up with, and I'll go back and emphasize that, what we end up with our signal-to-noise ratio is still about 3 times what it was when we took one exposure. More or less, the rule still holds. If you want to double your signal-to-noise ratio, you have to take 4 times as many exposures. The square root rule still holds. Read noise has a small effect on that and lowers it a little bit. So actually the best you could do with no read noise would be the square root. You actually do a little bit worse. But the real problem is that the sky glow and the thermal signal set you back at the beginning. So you're squaring off of a smaller base. So if you look at that on a chart, whoa, that does not look what it was supposed to look like. But all right, let's see if, oh, good, it got saved on the next one. All right, excellent. So if you look at the blue line at top is plotting an imaginary, and the shape of the curve is exactly the same no matter what numbers we put on here. These are just example numbers. The shape stays exactly the same. No sky glow or thermal signal at all. That's our sky glow and thermal will be what we call our unwanted signal, non-target signal. If the unwanted signal is the same as the target, which is pretty much approximately what we were looking at with our example, you see that it's reduced about 30%. If the sky glow and all the other unwanted stuff is twice the target, it's really more like 40%-ish. I didn't do these exact calculations. The reason why is because you have to think about these things logarithmic. This percentage drop doesn't matter. So if it reduces it by 50%, which is I believe the case if the unwanted signal is 3 times the target signal, this is reduced by 50%. But that doesn't mean you take twice as many exposures. To make up that difference, you have to take 4 times as many. So if you look at this, right, so if with no sky glow, in this example, you'd have to take about 12.5 minutes worth of exposure to get a signal-to-noise ratio of 35, right? To get that same signal-to-noise ratio, you have to take twice as many exposures if the sky glow is the same as your target. If the sky glow is 3 times as much as your target, you have to go 4 times longer to get the same image quality, the same signal-to-noise ratio. And this is before accounting for read noise, which actually sort of puts a damper on all this and makes all of it a little bit worse. So as I was putting this slide together, I was thinking, is 3 times the brightness of an object really reasonable for sky glow? Is sky glow really that bright? So I wanted to quantify exactly how bright sky glow was. So you're probably not going to worry about sky glow when you're looking at the brightest parts of your images. But in the dimmest parts, sky glow is probably going to overwhelm in a lot of cases. So I wanted to know, like, how does this actually play out? So this is the current sky glow or light pollution atlas, I believe, 2006 model for the East Coast. You can see on here very clearly New York City, right? You've got Baltimore and DC down here. We are here. There's Philadelphia. We are in a deep orange, umber. I don't know what to call that exactly. I'm just on the other side of that line, unfortunately. So I'm going to say that I'm in this area here, this orange. That's about a 19.5 magnitude per square arc second. How many photons is that? So I got to wondering, like, how many photons? I said earlier, I was looking at a dim object through a narrowband filter. I was getting 40-ish photons a minute. How does that compare to this? So let's do the math. So there's a great site, a Cornell astronomy class that talked about estimating the number of photons. So I'm using their benchmarks here. Magnitude 0 stars at the top of the atmosphere in V band are about 11,000 photons a minute. That's per square centimeter of aperture, per square arc second of sky, per nanometer of passband that you're looking at. That's at the upper atmosphere again in V band. Atmospheric loss around 10% is a good benchmark for that, and that gets us to an approximate, let's call this a rule of thumb, of 10,000 photons per minute per square centimeter of aperture per square arc second per nanometer of passband, right? That's a pretty good rule of thumb. So we are currently at, let's call it 19.5 magnitude per square arc second where we are here. How bright does that work out to exactly? So if you do the math for the scopes that I showed you at the beginning, my current preferred scopes, you got about 40 square centimeters of area. The pixel size works out to, I typically bin 2 by 2 when I'm shooting narrowband. You're just absolutely starved for pixels. So I bin 2 by 2 and I try to dither and make up the difference later on in processing. That works out to 41 square arc seconds per pixel. Magnitude 19.5 is 63 million times dimmer as magnitude 0. So you do the math there. 2.512 is the factor. That's the fifth root of 100 because every 5 steps in magnitude you get 100 times brighter. So the fifth root of 100 is about 2.512. You take that to the 19.5 power, you get 63 million. So running through the math, we got 10,000 was our benchmark, but we got to divide that by 63 million because we're at actually magnitude 19.5. We're going to multiply that by the size of our aperture, multiply that by the square arc seconds of sky per pixel, multiply that by a 60-second exposure, and then multiply it by 5, because I was using a 5 nanometer passband narrowband filter. Works out to about 77 photons per minute. Now, it's really bad. If you use a regular RGB filter, the passband's about 100 nanometers. You're looking at 1,500 photons per minute. So if you're looking at an emission nebula, it's only emitting in a couple of wavelengths. All its light is coming in that narrow band. You're still only going to get 42 photons or whatever it is per minute, and you're going to be getting 1,500 from sky glow. So you're looking at 30 times as bright. It's not 3 times as bright in a lot of cases, especially for emission targets. You're looking at 30 times as bright. And this is all under ideal circumstances, right? So this is at the zenith. This is looking straight up. This is with good transparency and assuming you don't have other sources of light pollution like the moon. Is this true? Does the math work out? I said, let's go check. So I looked at some exposures and I said, okay, the quantum efficiency at the H alpha line on my KEF 8300 chip is about 45%. You lose about 10% of the photons coming through the optical system, and you lose about another 10% on the surfaces of the filter. Let's say you're looking for an order of magnitude here. So by that, it's 36% total efficiency. I said 77 is what I would expect. Let's multiply that by 0.36, and we should expect about 28 electrons per minute. I looked at a couple of exposures taken at exactly those parameters. I measured 375 electrons for 20-minute exposures. That's about 19. So actually the math worked out pretty well. So 10,000 photons arriving at magnitude 0 probably is on the order of magnitude about right. Now that's going to vary. Your sky glow has different colors, right? So it's going to be brighter in different bands than others. Actually, your actual sky glow is going to vary by night depending on the humidity and all these other things. But it turns out it works out about right. But the bottom line here was that the sky glow for a lot of objects absolutely dwarfs the number of photons that are coming in. And this is why I love narrowband imaging. So this is, that's on the cover of the atlas. I believe that's SH2 132, sharpless 132. Over here in the oxygen area over here, I mean, we're really talking almost single-digit photons per minute. The oxygen line is a lot dimmer than H-alpha. Sulfur is as well. Really, really small numbers coming in there. So dealing with light pollution and trying to image something like this, this object, by the way, was the inspiration actually for doing the atlas. You won't find sharpless 132 in most atlases because it's almost invisible visibly. It only, this is a very dim emission nebula, and you'd have to have almost no sky glow and a really nice telescope to be able to see it. So that was actually the inspiration to create that atlas, was because I couldn't find that object, and I'd seen some pictures of it. I'm like, where is it? It's not even plotted. And it got me thinking about, okay, what about the really dim stuff? So with narrowband filters, you can get rid of 95% of the sky glow without getting rid of any of your target signal. So if you have 50 photons coming in, would you prefer to have 77 coming in from the sky glow or 1,500, right? And that's what narrowband filters allow you to do. They even allow you to do it on a moonlit night. And this is just sort of an illustration in the book that I put in to make this point, right? On the left, this is the effect of a filter on target signal. So that is basically the bandpass. That's that 5 nanometer bandpass. That's the light that the filter is letting in, centered right on that H-alpha line, or it could be centered in some cases right on the O3 line. So the light that the nebula is emitting, it's only emitting those couple of lines. That's all it emits. It's not a broadband target, so it's not emitting a lot of light. And it's all coming in here, so you can isolate it. So when you put the filter on, you don't really lose that much. But the effect on the sky glow, which is broadband, is dramatic. You've just eliminated 95% of it. So you've solved a lot of the problem that we talked about, where if your sky glow is brighter than your object, you're losing your signal-to-noise ratio. So I just put a slide up just to pay in passing some remarks about noise also exists in 2 dimensions. So pixel non-uniformity of response is important. So you have dark signal non-uniformity, so you've got hot pixels and cold pixels. And then you've got pixels that just don't respond the same to light. You got the fixed pattern noise across your sensor. We don't need to talk about it too much, A, because the concepts are similar, but also it's pretty easy to fix, right? So if you take lots of darks, take lots of flats, take your flats accurately, and you dither your images, you can pretty much get rid of most of the fixed pattern noise. And in fact, that's one of the reasons why, even if you have an extremely low thermal noise camera, you still need to take darks, because that allows you to remove the fixed pattern. So, or at least you need to dither. If you don't take darks, you at least need to dither. Otherwise, the same pattern of pixel non-uniformity is going to appear, and you can stack it over and over on top of itself. You want to move that around so it's being stacked and canceling itself out, right? But there's not that much to say about it. So that's signal-to-noise ratio in the real world. Now let's move on to 2 dimensions. So resolution and sampling are 2 interrelated topics in the 2-dimensional world for imaging. And resolution in particular, because it's the core trade-off that you make with signal-to-noise ratio. So we just talked about how we want to improve that signal-to-noise ratio as much as we can. The trade-off that you're constantly making, given the same amount of time, is typically with resolution. So you can do that multiple ways. You can bin your pixels or buy a camera with bigger pixels, right? That's going to capture more photons. You got more area, you got a bigger bucket, you're capturing more photons. You're going to get a more accurate read on that exact brightness. Your sample size is larger, right? Your signal-to-noise ratio is going to be better. But to do that, you had to give up resolution. You can basically do a similar thing. It's not quite as effective. Just display your images really small. If you take a noisy image, you'll find that a postage stamp version of it looks pretty good if you show your friends. Might not be the one you blow up and hang up in your office, but actually be suspicious when people post tiny little images, because that might be as big as a resolution as that image can be shown at. Focal length and focal ratio are another way you make that trade-off. We're going to talk a lot more about that in a minute. And then finally, blurring and noise reduction algorithms are also something similar. So think about what a noise reduction or blurring algorithm is doing. It's going from pixel to pixel and saying, okay, you're really high, you're really low, you're really high, you're really low. I'm going to sort of average you guys out and smooth that out. That actually improves your signal-to-noise ratio. The image looks less noisy visually, but you just did that. A blurring is nothing but losing resolution. Right? So this is sort of the fundamental trade-off that you face. You can have a great signal-to-noise ratio at low resolution. You improve the resolution, typically your signal-to-noise ratio, the image is going to look more noisy. Okay? So let's introduce another character. This is Harry Nyquist, and another unintended scientific paper for having implications that change the world. Right? So Harry Nyquist writes this paper, Certain Topics in Telegraph Transmission Theory. He was interested in how much signal you could cram down a telegraph line. Turns out that has been one of the most important concepts. It's now called the Nyquist-Shannon theorem because Claude Shannon went on to further expand this. But this is very important in sampling. So his idea, and he mathematically shows this, is that you have to sample at twice the rate of the smallest detail you want to resolve. And the classic example of this is that the human ear can hear up to almost 20,000 hertz. So CDs are sampled at 44,000 hertz. That's the minimum sampling rate that you could have to still recreate the original signal with any accuracy to be able to detect a difference. That's the minimum. You're not going to do it perfectly, but it would detect a specified difference. So when you extrapolate this from one-dimensional telegraph lines to a two-dimensional image, it still pretty much holds. There are conflicting opinions on what exact ratio you should use. I've seen 2.35. I've seen some very specific numbers. But rest assured that anywhere between 2 and 3 is about the limit. If you try to sample, if your resolution is more than 3 times smaller than what you're trying to resolve, you're wasting your time. And we'll show why. So undersampling is a choice you can make. You can choose to have big pixels. You can choose to have a really short focal length and make that trade-off and say, I'm going to give up resolution. I don't care about square stars. I don't care about a little bit of loss of detail. I'm going to give that up in order to improve the signal-to-noise ratio. And that's exactly what I was doing when I was imaging at 6.4 arc seconds was my image scale. Right? I was bending 2 by 2 on telescopes that are only 350 millimeters in focal length. Right? I'm willing to do that because I'm chasing after that oxygen 3 signal, which is literally like single-digit photons coming in a minute. I have to. So you can choose to do that, and that's a fair trade-off. However, if you are oversampling, if you are taking a chip with teeny, teeny, tiny photosites, or imaging at a really long focal ratio, and you're past the point at which your true resolution will support, you've brought your signal-to-noise ratio down in every photosite, but you didn't actually resolve anything more. Right? There's a resolution of the sky, there's a resolution of your optics. You've tried to exceed it. You're not getting anything more, but it's costing you your signal-to-noise ratio. Your image is going to look worse. That's always bad. So how do you know when you're oversampling? Well, let's use 3 as a benchmark. 2 is not a bad benchmark either, somewhere in that area. But if you're more than 3 times, if your image scale is more than 3 times smaller than the resolution that your skies and your optics are going to support, you're probably oversampling. And there's a very easy formula you can use to calculate what your image scale is. That's image scale in arc seconds, focal length in millimeter, and pixel size in microns. How do you know what your true resolution is, though? Well, for most people, it's the atmosphere. But there are actually several different limiting steps. So let's look on the left-hand side. You see, this is out in space. These are your 2 stars. This is what we're going to try to resolve. We're trying to resolve these 2 different stars. They're equal brightness. They're sitting out in outer space. Their light passes through the atmosphere. Let's say you're on Mauna Kea or you're in Sedona, Arizona, or any of the places we talked about. Probably going to survive, depending on how close those 2 stars are together. Now, you've got great optics and large enough aperture to support it. Aperture is no matter how great the optics are, aperture does provide a limiting step for the minimum resolvable size. And then you've got a sensor with small enough pixels to tell the 2 apart. That's basically the minimum minimum you can do right there. That's where the troughs of the two stars, they overlap, and you can just barely tell that there are two stars there. That's sort of perfect resolution. In most cases, the atmosphere is your limiting step. So it gets blurred here. At this point, it doesn't matter if you have a huge aperture. It doesn't matter if your optics are perfect. It doesn't matter if your photosites on the sensor are incredibly small. You're not going to resolve anything beyond what the atmosphere is already blurred. You can't resolve something that's already blurred. This example, let's say that the atmosphere is great, but your optics can't support it. Either the quality's not there, you're not in focus, or actually just could be the aperture's too small. Smaller aperture does not resolve as much. Doesn't matter what you do with the sensor here. You're oversampling if your pixels are too small at the sensor in this case too. Finally, you can have great atmosphere, crystal clear optics and aperture to support the resolution, and your sensor pixels are just too big. This is a choice you can make. That's where you've deliberately decided to undersample. That's not so bad. I didn't mention on here your mount. That's another source, right? If your mount's not stable, everything else can be good. And again, it's introducing a blur over the course of your exposures. So in most cases, 2 to 3 arcseconds seems to be a pretty good benchmark. Unless you live in the desert, you can assume 2 to 3 arcseconds probably for your sky. You can measure it, and it's going to vary night to night. But that tells you then, and this is a chart that's in the book, you can calculate, or you can just use the chart and say, okay, I've got pixels that are 6 microns. I'm imaging at 500 millimeters. Looks like I'm probably around 2 arcseconds per pixel. I'm good. If you've got 3 arcseconds seeing, you really, if you get much below 1 arcsecond per pixel, you're probably oversampling. So this is color-coded to be a rough guide, right? This is for average skies. If you're out in Arizona or something, you could probably get away with a lot more. If it's a really bad night, you might be oversampling all the time. But that just gives you a sense of resolution and sampling and how they matter. Now, I mentioned focal ratio in there. Focal ratio should come with a warning on it. And this warning's not for you. This warning's for me. So talking about focal ratio seems to stir almost partisan political passions among people. They get very, very upset if you don't take their particular view of this. So my approach here is to try to take the same approach as before. Let's try to see if we can develop an intuitive approach to this, okay? So this is the Cone Nebula with the whole Fox-Fur area around it in H-alpha. For some reason, I've seen multiple examples of people using this as in a lot of these single pixel examples. So I thought I'd throw this one up here. Plus, it's just kind of a nice black and white picture. It's one of those objects that does well even in black and white. So let's take a little patch of the sky from the Cone Nebula there. And we're going to look at aperture. So aperture will determine the brightness of the object, assuming that you hold focal length the same. Okay? Makes a ton of sense. You've got a giant lens at one focal length that's going to gobble up more photons. You've got a bigger area. You're gathering in more photons. Put those at the same focal length. It's going to be, with the smaller aperture, you're going to get a dimmer image. And maybe it even helps to sort of think about this as like a camera obscura or something, where you're projecting an image onto a white screen instead of like sort of ignore the pixels for a minute. Like, right? That makes sense. You got a smaller hole of light coming in, and you're going to have a dimmer image. Totally makes sense. Focal length is what determines the angular resolution that you have. Basically, that means it's determining the size of the projected image on that wall. So if you take a shorter focal length and your sensor size remains the same, you're going to get a wider field of view. If you hold aperture the same at the same time, you're actually going to get a brighter image too, because you're gathering the same number of photons, but you're concentrating them into a smaller area. That's going to be brighter. That's more photons per photosite. What we've done when we did that, though, when we reduced focal length holding aperture constant, we just reduced the focal ratio, right? So focal ratio is a unique value that actually determines the rate of flux at the sensor. So you're basically covering more sky and you're cramming it into a smaller space. So you're taking photons from a larger region, cramming them into a smaller space. You get a brighter image, more photons per photosite. That's holding aperture the same. That's all obvious, right? But I said focal ratio is uniquely able to determine the flux per sensor area, the brightness per area. So if you were to do the experiment where you went outside and you took a tiny telephoto lens, or even a 50 millimeter lens, and took a picture of the Andromeda Galaxy at f4. You took a large telescope, and took an image of the Andromeda Galaxy at f4 with the same sensor. It would be the exact same brightness per area on the sensor. You took a 1 minute exposure on each of those, it would look the same brightness. However, obviously, with the 50 millimeter lens, it would be tiny. Your resolution, you've made that trade-off between resolution and signal-to-noise ratio. But focal ratio uniquely determines the brightness at the sensor. All f4 systems, assuming same reflectivity and efficiency and everything, will produce an image that is the exact same brightness given the same exposure time. Again, imagine you've got, you're projecting onto a screen and the pixels aren't there. You're just projecting onto a white screen. You're going to get the same brightness when you look at that. It's just going to be a lot smaller. So focal ratio does have a unique value there. So this is how I think about focal ratio. Focal ratio, it's a measure of how you're concentrating the light. It's a measure of what you're doing. At apertures, you're capturing so much, but and focal length is determining how small of an area of the sky you're looking at. Focal ratio is saying, how am I concentrating that? It's a way of asking or answering the question, do I have the aperture to support the focal length that I'm imaging at? So I mentioned up front that my early experiments with that f15 Maxitov Cassegrain, things like 2,500 millimeters of focal length, and 7 inches of aperture just isn't enough to provide what you need at that resolution. You're looking at teeny tiny objects. They don't produce that many photons. They take up a tiny area of the sky. You need a big aperture, which basically means you need to hold your focal ratio constant. So a lot of the debates on the internet seem to focus on this idea of object signal-to-noise ratio, which is the signal-to-noise ratio per angular area of the sky. That's true. That doesn't change. We don't take pictures in terms of angular area of the sky. We take pictures that are composed of photosites. They're composed of pixels. And each one of those has to get enough photons to overcome the read noise. It has to get enough photons that you get a reasonable estimate of the long-term photon arrival rate, which is the brightness of something. So that's how I think about it. Note that you can do something similar with binning, right? Binning is allowing you to sort of take in more photons. It's basically getting an effectively larger pixel with only a slightly larger read noise. And it definitely can have a similar effect. It's not going to increase your field of view. It's actually not quite the same because you don't get 4 times the read noise when you bend 2 by 2, but you do get twice as much read noise. So it's not perfect, but binning on the camera can help with that. Binning after readout, it's just the same as it's just shifting your image size. That's all that's doing, and that can, if you print it the size of a postage stamp, it's going to probably look a lot better. But you didn't actually change any of the noise characteristics. Your signal noise ratio in that image is still exactly the same. Whereas binning on camera can actually give you some benefit in signal to noise. Okay, so we've covered Poisson, we've covered signal to noise ratio, cameras, resolution, Harry Nyquist, we've covered focal ratio debate. Let me just take a look at a couple of images here to prove this point before we bring it home. This was taken, I think this was this January. This is only 2 hours of exposure. This was taken with a 48 millimeter telescope, also known as a Samyang 135 telephoto lens at f2.8. So you're talking about literally this much aperture, and in only 2 hours. It pulled in a ton of photons. Why? Because it's pulling from a large area of the sky, which basically means great focal ratio. You're looking at f2.8 here. It'll open up to f2, but it's not as sharp. So there are a lot of objects in here that you could image on their own with a larger telescope. and you probably should if you just want those individual objects. Right? So let's take the smallest one here, M78, and zoom in on it. That's not going to win any awards on its own, right? So 48 millimeters of aperture is not really enough to take an image of an object that small. In order to take an image of an object that small, you need a much longer focal length, which means you're going to need a much larger aperture to maintain the same focal ratio to get that same brightness, right? But the point holds that the brightness of this object, if you were to image it at f2.8 with a very large telescope with a much longer focal length and better resolution, with the same 2-hour exposure would be the same brightness. So focal ratio does have a unique ability to determine how long your exposures are going to be, and going fast has been one of the things that made my life so much easier. You saw that progression telescope, they got faster and faster and faster. When I got that Borg and it was at f4, it was like a revelation. It was unbelievable. Everything, it was just like I couldn't believe suddenly narrowband was working. Everything just clicked, right? So let me summarize all of this. Let's see if we can sort of condense it all into 5 quick takeaways, 5 practical takeaways, okay? First one is go long. You need as many target photons as you can. I said at the beginning, if you just gave the advice to just take longer exposures, that's always going to improve your imaging, right? But think about it. The objects that we take pictures of, there are already thousands of pictures of them. If you're thinking of your night of imaging as I'm going to take a picture of this for 2 hours, I'm going to jump over here and take 2 hours of this, it's great practice, but the only way to make an image even remotely stand out is to get a lot of photons in there and try to go deeper, or at least as deep as other people have gone before. So think like 10 hours, think multiple nights, think projects, and see what happens and watch what happens to your imaging. Your processing and post-processing gets so much easier when you have great signals-noise ratio and you have great data to work from. That comes from taking multiple nights. Think 10 or more hours. Go fast. Your life's a lot easier. If you have a fast scope, you're cramming in a lot of photons per photosite. Everything also gets easier there. Go cold. The benefit of a cooled chip partially is the reduction of the thermal signal, but it's also the ability to hold an accurate temperature all the time. So when all of your darks are taken at exactly the same temperature as your lights, and you have thermoelectrically cool the chip to the exact same temperature, you're able to control that, your dark subtraction actually gets a lot more effective. That was one of the big revelations coming from a DSLR to a cooled chip. It was like, wow, yeah, the thermal signal did go down, but actually the dark subtraction seemed to have a marked improvement, right? And that's because it was the exact same temperature every time. Go steady. Having a great mount is, you've heard the advice, you've seen it everywhere, right? Everybody wants to get a great scope, but getting a great mount is where you should probably spend your money first to then get the great scope. The great mount also just makes your life a lot easier. And finally, if you live in a place like this, really adding narrowband filters to your arsenal is something that allows you to image with almost no disadvantage to somebody who's in a desert, other than the fact that we only get 30 clear nights a year, right? You can cut through that sky glow in a pretty amazing way. I shoot my oxygen and sulfur with 3 nanometer filters now, and I shoot H-alpha at 5. And with the 3 nanometer filter, even on a full moon, I can shoot oxygen 3. It's just amazing. So that's limiting you to a certain subset of targets, only emission nebula, but the payoff is that you don't have to deal with all the sky glow, and I can actually use the eastern half of my sky. All right, so I said at the beginning, this is an extraordinary pursuit. This is absolutely an extraordinary hobby. Doing astroimaging, astrophotography, chasing after individual photons that you can literally count is something absolutely extraordinary, and I think the results are extraordinary as well, so I encourage you to go out and pursue it. Thank you. Any questions? Yeah?
I have 2 questions.
Sure.
One is, how do you do that with a dual scope?
Yeah?
And number 2 is that if you imagine a read noise-free camera, could you do, instead of doing a 30-minute exposure, is one 30-minute exposure same as 31-minute exposure?
Yes.
On a read noise-free
On a read noise-free camera, yes. They should be functionally the same. Yes, so you could divide it up however you wanted. If you have no read noise, there's no per penalty exposure, and you're getting a perfect count of the photons each time. Sure, you can the shot noise will accrue, the same as when you combine those exposures in the end. As far as having two cameras side by side, you can still dither, just the dithering is equal for both. So what I'm doing is I'm not shooting the same channel in both cameras typically. I'm shooting oxygen 3 all night in one and let's say H alpha in the other. Or I'll even shoot like RGB in one camera to get star color and then one of the narrowband channels. But they're both moving together on the mount at the same time. So I can dither them both at the same time and the effect is the same in the end.
How do you get the exposure times to, how do you start one, or do you do it manually?
No, I start them, like I'll start 20-minute exposures at the beginning of the night, let's say, for both of them. Actually, I stagger them by a minute just to make sure that the USB cable, I run them in my front yard, like 30 feet from my front door. So I've got this long USB cable, and I stagger them by a minute so that when they read out, they're read out about a minute apart so that the two aren't trying to download across the cable at the same time. But other than that, no, I just I start them both, I have them both going at the same time. Yeah, so the color channels are, over the course of a couple of nights, it's going to average out the dithering. You're not going to see the effect of dithering like you'd expect there. Yeah?
What do you use for image acquisition and dithering and guiding?
Oh, man. So for image acquisition, I can't believe I'm saying this, but I use the software that came with the SBIG camera CCD soft. Yeah.
How do you dither them?
So typically what I'll do is with the CGEM dithered for me.
Yes, it did. Very well.
Right? It dithered for me. It just didn't track super well, and it was blurring a little bit, but actually the results weren't that bad. I found that with the EM200, I'm going to have to move to, and I just got this just over 6 months ago, I'm going to have to move to a more sophisticated platform for acquisition, because unless I mispolar align a little bit, and you actually naturally get a little bit of shift anyway, if I accurately polar align, I'm going to have to add the dithering back in. I was relying basically on either poor mount gears or slight errors in polar alignment to do the dithering for me. I can't do that anymore.
Have you looked at Sequence Generator Pro?
That's my next purchase probably. Yeah, yeah.
I actually saw
Gets great reviews. Yeah.
And it'll do the capture and the dither, and it actually uses PhD
Yeah.
guide, which is actually pretty good.
Exactly, and it'll calculate your mosaics and do all sorts of other stuff.
Have you
Yeah.
upgraded to PhD too?
Yes, love
Yeah,
PhD
it.
too.
Oh, it's incredible.
Love it. Yeah.
It even tells you polar alignment, how much you're off.
It's terrific. Craig Stark did a great job on the first version, but the second version actually everything's faster. It seems to align faster.
They just released like a month ago. Or
No, I haven't tried that yet.
Okay.
Even better.
It's even better.
Yeah.
It'll set you up. You push a button, and it'll tell you all the parameters. It'll tell you how to change. It'll say you could do 5 seconds unguided. Change your guide
Right.
to 5 seconds or something like that.
That's crazy.
And yeah, it'll tell you
I-
then your stars. Oh, one more.
Yes.
Off-axis guider, or you have a guide scope?
So I used to use a guide scope. When I got the QSI, I went to off-axis. So that has an off-axis, pick-off mirror on the side. Problem is, I changed from the CGEM to the EM200 about the same time. I went to off-axis guiding with the QSI. Between the two, there's a big jump in improvement, probably from both of those things. So now I do off-axis. Before, I used to use just, and I still use it like with the telephoto lenses and stuff. It's literally just a 50 millimeter, the little basic, the Star Shoot package that Orion has. It works great. And actually, I've moved to a QHY, much more, the 2L mono. It's probably 10 times more sensitive.
I just started that.
Yeah, it's way better than the Star Shoot, which was where I started.
I'm trying to sell
Yeah.
the Star Shoot. Nobody wants to buy it now.
It's old technology, man. Times move on. Yeah, I know. Yeah. Any other questions? All right. Well, thank you guys very much. It's been terrific to be here. I appreciate it. Thanks.